Welcome everybody to this series of web seminars on applications of geometry and topology, and it's a great pleasure for me to deliver this lecture on these aspects, on devilish aspects of geometry that pops up maybe sometimes unexpectedly in topological dynamics. As you see, I'll immediately show the picture of something that is not devilish at all, is rather angelic. It shows optical caustics in water. These are just strange effects of optics, of light going through water. And perhaps these are reminiscent of more dramatic changes that we may have in fluid flows or during continuous deformation of fluids. So I will emphasize on aspects of fluid flows in different contexts. But this pretext gives me the idea of leading you to another example, which is the pinch-off of a bubble in, say, water on soft matter otherwise. And the pinch-off is a more dramatic change of topology, of course. So we go from a system to another. Still, in terms of energy, we may not care much about. But we may have changes that are more dramatic, both in geometry and in energy contents. And these are represented by these enormous, gigantic energy bursts in solar physics. So imagine that this disk that you see is covering the sun, and this is, imagine that a little dot on this slide is the Earth diameter. And so this gives you the idea of how damaging can be energy burst of this size. Now, I thought that the topic of investigating a little bit the troubles that are behind angelic deformation of fluid flows is an interesting topic and gives me a way to pay tribute to maybe work that we've done with Keith Moffat over so many years. So I think I like to talk about this in some detail and show you, hopefully convincingly, that what I like to address your attention actually takes place in several contexts, either hidden by the physics because energy is almost negligible, or so evidently shown by these gigantic energy bursts in plasma physics. So to start, let's just review the progress that we've been doing in all these years, 150 years of what we may call topological dynamics or topological fluid mechanics, if you like. And no doubt that one of the most important contribution came from Gauss, 1833, with his linking number formula, as many of you know. And with that, more or less the same time, the knot tabulation by Tate, Gauss lamented the slow progress of what was known at the time as geometry of position, that listing introduced as topology, and Tate in things. And all this was accompanied by what we may call applications or interests in applications. And that came from Maxwell. Maxwell was behind Tate, and although new books on Maxwell's life and contributions came out recently, I think nobody really noticed how much Maxwell's work was behind Tate's tabulation, and that is really discussed at length by several letters, private correspondence between Maxwell and Tate. So Maxwell was keen on applications, and he thought of applying ideas possibly to magnetic fields, and that was in the wake of the applications to vortices that Kelvin's had in his theory of the vortex atom as a theory for particles, for matter. And that was done from 1867 till 1880s, more or less. And even the discoverer of the electron worked on that, J.J. Thomson, who got the Nobel Prize for the discovery of the electron, 1906, but in 1882, got an Adams Prize in Cambridge. He was a Trinity man, and for his work on Kelvin's vortex atom theory. Well, that is roughly what we may say the beginning of what we may call topological fluid dynamics or topological dynamics, and it developed to modern times in many different directions. We have searched for knotted solutions to Euler equations in many ways. For example, fluid topology in 3D case is very hard. Only very recently we had some interesting results. Solutions to vortex dynamics in terms of knots or links, and these are also extremely difficult to find. We have a great deal of information about invariance, but what is the relation of fluid invariance, like kinetic energy, momenta, and other stuff, to the invariance of topology is still not so much known. And then about stability in various senses. More recently, in the last 30 years, we have work done on energy relaxation method, starting from magnetic structures to more wild structures, for example, electrically charged knots or the signals from knotted antennas, etc., etc. And that led also to work on ground state energy and relationship between ground state energy and topology, which is relevant in modern string theory, for example. Then the purest approach from dynamical systems considered, and of course volume-preserving flows considered existence theorems for vector fields or orbits that are not only chaotic or closed, but they form really complex topologies. And again, we see the structures in terms of Hamiltonian that might be linked with fluid invariance in Euler equation or not. So the idea is to relate various topics here in the context of conservation of topology. But, of course, if we include dissipative effects and viscosity, resistivity, etc., we, of course, have a change of topology. And so the theme is to understand, to discover the role of all these features when topology changes. It changes through, technically speaking, surgery of mathematical structures like knots and links, or what in physics is referred to reconnection. And through reconnection, you can explore change of topology and relate that to the change of energy, which is ultimately an important aspect, a fundamental aspect in all physical theories. Now, in mathematics, you are left with a challenging problem of singularity formation. And all you know the importance of this problem in considering the finite time singularity formation in fluid equations, in Navier-Stokes equation, and of course in the related inviscid form of Euler equations. Well, if we want to just for simplicity set a scene, we may consider diffeomorphisms of frozen fields. This is just help us to make some progress in the field of fluid mechanics, if you like. If we take ideal, incompressible, perfectly conducting fluid in an infinite domain R3, we consider a velocity u, function of a position vector x and time t. And we assume, again, for simplicity, divergenceless condition in this space, and u at infinity going to 0. Then fluid flows according to what is called a torsion field evolution. Fields like magnetic fields or vorticity fields evolve according to an equation that is rooted in the 19th century science, is recognized here. If you think of the magnetic field, you see this equation is Faraday's equation. If you substitute B and you think of B as vorticity, so if you substitute vorticity here, you see the equation that is known as Hellmuths equation or vorticity transport equation. So this is the class of fields that have been considered in so many contexts in these last 100 years. A change of the field in time is controlled by this part of the equation, and if vorticity is replaced, here you have a relationship between u and vorticity, vorticity being the curl of u, which makes this equation terribly difficult for the nonlinearity present. If B is the magnetic field, then you may think that the magnetic field is just transported by this change in time according to this equation, and the fields, vorticity, magnetic, etc., are divergence-less and with a finite energy. Well, these, as I said, 100 and plus years of this equation means that these equations have been much studied, and we can trace back the formal solution to this equation even to the time of Cauchy. Indeed, we can express this formal solution to this equation as Cauchy solutions. And these Cauchy solutions are really essential for our discussion on topology and continuous evolution of fields. Why? Because we take the field at time t equals 0, initial position, and a given configuration x0, and this field is transported by this quantity, and this quantity is inherited by the assumption that everything is continuous and has an inverse. And because everything is continuous with its inverse, we can always map the original field to the final field. So this establishes a correspondence through this deformation tensor between initial configuration and final configuration at time t. So we establish a topological equivalence class between fields. So suppose, like a plastilin, we have something that can be continuously deformed, then you play with this plastilin. It's like a dead body. You play with that and you deform it to this without cuts. I'm sure some of you wonder how it's possible to deform this to this without cuts, and this defies our imagination. If this were as we can think of, if it were made of a fluid or as indeed a plastilin, we could do this. How? Well, the answer comes, this is a picture taken from an old book by Prozolov, the American Math Society booklet on changes of topology and topological transformations. Well, it can be done, as you see, by deforming this handle into this, and then further deformation by just stretching this handle into this shape. Now, it's interesting to pay attention to this. If you are keen on, say, continuous deformation, you would say that this passage from the second to the third stage is just angelic. You can think of it as a rider-master move in 2D, if you consider the orthogonal plane to the slide, and is a kind of ambient isotopy. But what about transformation of this into that, or this into that? Well, definitely here you may have a rider-master type 1 move playing a part here and there, because you have to think that there is a twisting of the yellow matter in this plastilin. And likewise here. So everything is continuous and can be deformed continuously. But something must be more trickier. Well, let's consider localized fields. Localized fields as physical knots and links, and that gives me the possibility to talk about something that involves twist. Well, localized fields can be modeled by tube. So think of a tube as a tubular neighborhood of a central line, C, and the cross-section, for simplicity, let's say, stays circular. And the volume, so, is well defined of this tube. And now in R3, we can embed this tube with a field. And the sup of this field, say magnetic field or vorticity, is just inside this tube. Well, we can even foliate this tube with solid tori and asking this condition to be fulfilled on each tubular surface. This condition says simply that the field has no normal direction across the tube boundary. That means that the tube boundary, or every single tube boundary within these foliations, is a material surface. Well, of course, this is a model. So we can define a link or a knot as a physical knot, or link as a smooth immersion to R3 of a number finitely many disjoint standard solid tori. Okay, this is just the beginning. We can think of this as a field going inside this tube, and through the cross-section, therefore, we have a flux. So we consider particular deformation that conserve volume of the tube and the flux within the tube. And the flux is just given here as the product of the field B, say, along the longitude direction, along the axis of this tube. And these two quantities, the volume and the flux, we take it as the signature of the deformation. All right, so there are lots of results about physical knots in recent years, and I'll focus on two in particular. Well, magnetic energy. Well, magnetic energy, in the case of magnetic fields, we can define magnetic energy by this formula. This is a standard definition. And then we have helicity. Helicity is h of t, t being time, and we can define it as the integral of a dot b, a being, you see here, the potential associated with the magnetic field. And we can set a Coulomb condition for this vector potential to be div A equal 0 in R3. Mind you, the volume is the volume where the field B is defined. Now, why I care about these two qualities? In this context, helicity is conserved in time, i.e. h of t is just h. And with this in mind, we can establish a relationship that is due to my former supervisor, Moffat. Keith Moffat, 1969, has an important paper establishing a fundamental a fundamental relationship between this invariant quantity h conserved for fluid flows, for fluid mechanics, given by this integral, in terms of topology, in terms of conserved quantities of topology. Namely, if fields are localized in tubes, knots or links, then this relationship can be expressed in terms of linking numbers. In particular, the Gauss linking number between, say, a tube I and the tube J. The fluxes phi I and phi J are also conserved. And additional contribution comes from what we may call the self-linking number of a single structure. Now, if we reduce this equation to one single contribution, we can focus on helicity made just by the linking number, the self-linking number, times the flux squared. Well, this is well known, is known to be the Calugarianu White-Fuller invariant for single physical knots or links or ribbons. And this self-linking can be written in terms of writhe and twist of the tube. Well, the writhe has this complex expression, and if you pay attention to its structure, you can recognize the integral being the integrand being basically formally identical to the Gauss linking number integrand, and the exception is that here for the writhe the double integration is over the same curve C, C being the axis of this tube. And then we have to consider, so this is a geometric information, is the geometry of C that gives information for the writhe, and writhe being in a sense a measure of the three-dimensionality of this curve C. However, around C we have other field lines or other structures, so we refer to a ribbon exemplified by this little ribbon here, and the ribbon is brings in a framing for the mathematical knot, so it makes it a physical knot, and the framing is given by the relative twist that this ribbon has with its center line. And this twist, again a geometric information of the ribbon, can be split in two quantities: total torsion and intrinsic twist. And total torsion given just by the normalized total torsion of the curve C. And finally we have the structure outside C given by this ribbon here, and in particular for field lines represented by intrinsic twist. Well, what's interesting is to consider physical knots, and so I'll just give you an example of a physical knot more in detail to show you what we have in mind. So consider a flux tube model, as I mentioned before, but we have to go a bit more in detail. We imagine that the magnetic field is made of two contributions, one poloidal and one axial along the longitude. And we still assume there is a dependence on R to give this model some generality. We revert the field description in terms of fluxes, poloidal and toroidal, or meridional and longitudinal fluxes, and evidently we can then define a twist given by the ratio of these fluxes. Now, if it were a physical magnetic flux tube, then it would be subject to a force. So it would evolve, it would move in the fluid according to the Lorentz force, and we can work out the Lorentz force using a little bit more sophisticated coordinates and known as Mercier coordinates. And the difference with the usual curvilinear coordinates is that the Mercier coordinates keeps the metric orthogonal. Anyway, we can figure out the perpendicular direction of this force, and the poloidal or meridional force on this flux tube. And to put everything together, we can see through here that this force actually, the meridional or poloidal component just doesn't make the flux tube move or drift in the fluid. But the perpendicular force has a leading order term due to the curvature times the principal norm. And so I reduce this force to this simple form, curvature along the principal normal. By doing so, immediately, for those of you keen on elastic systems, immediately see the analogy with the behavior of elastic bands, because also elastic strings are subject to this force due to elastic tension. Well, if we assume that the axial field is much greater than the meridional field, then you may think that actually on the flux tube the tension along the tangential direction on the axis is the leading order in your model. Well, in that case, if you take a magnetic knot in the shape of a trefoil knot as a loose knot, and you ask yourself what happens under this force, if the force is like this, assuming that the axial contribution is much stronger, then evidently you expect that the trefoil will shrink, and under conservation of volume and flux, it will get fatter and fatter until in time it will reach a relaxed state of a tight knot. And this is indeed the case, has been investigated, a number of papers have been written, and the investigation on tight knots bears a similarity with another problem, the problem of ideal shapes. But here I'd like to point out something else. I'd like to say, well, what happens if in the case of a loose knot we have a situation where the geometry presents inflections? In other words, when the geometry presents a change in concavity, then what happens during relaxation? Maybe at the very end state, at the very end relaxed state, the situation will be inflexion-free, and during this relaxation, the curve, the knot, must evolve in order to get rid of these inflections. Because as you see, the Lorentz force is pointing one direction in one case and the other direction in the other case. Well, inflexional configurations are the ones that we paid attention during my PhD with Keith Moffat, and indeed the passage through an inflexional stage is quite interesting. So I like to go back to that. Inflexional configuration is an intrinsic property of the curve and is given here by curvature equal 0. But if we want to investigate the generic behavior of these curve subject to some kind of kinematics, so t is not really a dynamical time, but is a kinematical time, we can Taylor expand a kinematical curve, so to speak, around c equals 0 and see what happens. So here we find the generic behavior of this passage through this inflexional configuration, and to our astonishment at the time was that torsion goes singular. You see, is a singular not only t but in s. Now it's interesting because this singularity, which is hidden here, is actually integrable. Is completely integrable over a small interval, both sides around the inflection point. And the jump in total torsion is finite. So it doesn't appear to be a problem. And that's why we can convert, in a Rider-Master type 1 move, continuously twist to writhe. We know this is, in this context, is conserved, self-linking. So topology is conserved. There is a continuous exchange of writhe and twist. But if we think of twist as a contribution from torsion and intrinsic twist, because everything is continuous and has to be constant, then a jump somewhere in the torsion must be compensated by an equal and opposite jump in intrinsic twist. And in other words, this hidden singularity is integrable, and it doesn't appear to create any problem at all. Well, if we want to pause again on these knots and links and physical knots and links, consider how to convert an inflectional knot to an inflection-free braid. Again, I'm not thinking of a dynamical system. I'm just showing you just changes in shape. So we can just play Rider Master Type 1 move over there and deform it again, and we can convert this configuration into that form. Of course, if I assume that there are inflections here, I can convert it to have an inflection-free form here. This form is often referred to as a closed braid presentation. It can be also mapped on a spherical geometry. Now, for applications, this is interesting. Look at this image, quite astonishing. This is an image of 2002 taken by a TRACE satellite mission, and it shows the emergence of a magnetic, of a plasma loop, should I say, that at a certain point, due to some twist, inherits from the solar, so to speak, photosphere or atmosphere, then goes up in the corona and twists up, and gets destabilized. Quite remarkable picture. Now we have lots of very detailed information about structures of these plasma loops. These are called coronal braids, and these are somehow the source of a great amount. 90% of the amount of energy we receive from the sun is due to this continuous eruption of these structures into possibly bursts of energy. Now, if we want to consider magnetic fields in inflectional states, then we can state the following. First of all, these are in disequilibrium, and you have to work out your Lorentz force under inflectional behavior. And so if we have inflections, and these represent just a braid over the solar surface, then if the amount of twist in this braid is below a certain critical twist value, then they relax to an inflection-free braid, one of the structures we saw before, one of these. If, however, the twist is above a critical twist, they are known to become kink unstable, they break up, and they release energy. That is the energy we get from these breaks. Well, inflectional states in applications play a role in many fields, and here is an idea about a very recent observation I presented at the conference. We have inflectional states for toroidal fields as well. Imagine that we start with our magnetic field line, that is a planar circle, and then we perturb this plane circle into a toroidal helix, or if you like, a toroidal knot. So here we have a torus with aspect ratio lambda, a small radius r over the large radius capital R. And as we do this process, somewhere inflections must appear. This is more evidently so if we consider this transition in terms of the tangent map and the indicatrix. So if we do the tangent map on this curve becomes the planar circle or the equatorial circle on the sphere. But if we map this new curve to the sphere, to the Gauss sphere, then our inflections are revealed as a sequence of cusps, a finite sequence of cusps, which is quite interesting phenomenon. Indeed, we investigate the number of wraps along the large and the small radius of the torus, then these torus knots have at least 2 points of inflections. And in particular, we can locate these points. And these points, for a uniform twist on nested tori present problems. And present problems for tokamaks. You know, tokamaks are machines made of a toroidal vessel, and in this vessel we have magnetic fields embedded, and if the twist is uniform as it is in the current machines, then somewhere on some foci of these toroidal surfaces, we definitely have a critical winding number that, i.e. a critical ratio of Q over P related to the aspect ratio of these torus that gives instabilities. So this is a very serious matter for people in fusion physics to be considered. Now I'd like to move on, but I wonder if I think we may pause a minute or two to have questions, if anybody has questions, before moving to something related, but a little bit different. Any questions?
Yeah, Renzo, I had a question. In the kink instabilities, these things, the field lines actually break, and so that's where the energy comes from.
Exactly,
so
they
it's not like a
definitely do.
reconnection event at all.
You know, when you say they break, they do break. You have to think of this as, in a simplistic way, my simplistic way, is in terms of Reynolds number, which is a measure of the importance of resistive effects or dissipative effects. And so in general, in the bulk of the fluid, you deal with Reynolds number of the order of even millions. So because what matters in the equation is 1 over this number, then it doesn't really matter. But when they are close to break, Reynolds number goes down a lot, so the inverse increases a lot, and is the region very close to the magnetic field lines where when they break. So in that region, you have a change in topology, and the change in topology allows you to have a change in the whole distribution of energy. So there is a change in energy due to this disruption of energy. Most of the energy is stored, you understand, is like, the braid is twisting up. So at a certain point, the field lines are twisted so much, they cannot stand too much twist. So this is the mechanism that leads you to the breaking. And you don't need that much twist, by the way. When I say critical twist here, I mean for the kink instability is more or less 2 full turns, is actually below that. So by 2 full turns, if it were an elastic band, you would think that it would break up. So you don't need that much. And this full turn, this twist, is inherited by the rotational motion on the solar surface. So it is convected through convection to the surface, and then the magnetic fields are rooted in this surface. So they inherit this rotation, this localized rotation. They make this rotation to be distributed as much as possible, I presume uniformly as much as possible in the braid, and then more twist comes up, and at a certain point they break up. These events can be disastrous and actually are a matter of great concern about of course, predictive models, because of the difficulty to have predictive models of these for these situations. It's like an earthquake. It's a release immediate burst of energy, and this is the energy that makes our sun flares our sun bright all the time, and so. Yeah. Okay. Let's move on, and here are my foliations, and just giving you the idea of the nested tori in a tokamak. Now, I'd like to not only pay attention to knots and links, but also to surfaces that are bounded by these knots and links. These surfaces, in particular, are playing an interesting role in certain contexts and physical applications, biological applications, etc. One particular type of surface is the Seifert surface. Seifert surface is an orientable spanning surface bounded by the knots, so we have to look for orientable surface. Now, in the case of magnetic fields, of course, these surfaces are potential surfaces, and we can identify these surfaces as a surface for the potential vector A. But what is interesting is that you may have a knot, say a trefoil knot, and you can deform it to another shape and then another shape. And what happens to the surface? To the surface bounded by this knot? Well, in this case, the first case here, we saw the same here, we know that this is not non-orientable. So being non-orientable maybe is not of great physical interest, because you have to understand that on one side you have some physical information that somehow you have to get on the other side. And also this is non-orientable. But this is orientable. So let me repeat, we may deform one knot into another or another shape. What happens to during this continuous deformation to the topological properties of the surface rather than the knot? You know, in this case we have orientability that breaks up. This idea is quite interesting. We can take, for simplicity, the case of the Unknot in this shape. This is a space curve that is unknotted, and you can think of deform it, and so that it evolves, and it evolves, this is just kinematics, and it opens up like a flower just to become a plain circle. Well, I was curious about something like this some time ago, and so I proposed to study this problem with Francesca Maggioni, and we came up with these equations that describe this evolution, and actually many more of these evolutions and many more complex types of these evolutions, extending lots of interesting geometric results on planar curves of 19th century Italian mathematics into 3D. So we published this time ago, and then a further step was to consider the surface and how it goes, this surface. Well, it's very hard to analytically describe this surface according to analytical equations, but certainly you can work out a surface starting from this geometry. So we take this curve and we consider the surface that can be developed or constructed based on these curves. Well, I was curious to find out what happens about this, so I talked to Keith Moffat almost 20 years after our first paper in Cambridge, and that was more or less 10 years ago, and he got very interested. And so we developed together an interest in this. This is the ruled surface that you get, is of course an approximation of something you'd like to study, but it shows that something weird goes on towards the end. Remember, the boundary curve continuously deforms from the first step to the final step, but the surface, we know the surface has to go through something bizarre, because we start from one-sided surface and we end up with a two-sided surface. Why not to make it a soap film then? Well, we played with soap film. Keith rushed to the city center to buy some liquid wash machine, and the machine was just some water and a piece of string, and trying to play with that. That was fun. But as you may guess, we didn't get much from that. Suddenly we realized that something bizarre was going on, and we started looking at literature. And these three sketches are not my hand drawings, but imagine whom. These are hand drawings of Courant. Courant did this and investigated this possible transition, inquiring about this bizarre possible behavior and the solution of it. And here is the man with his assistant playing with the soap solution. Well, the story of soap films is ridiculously short. Actually, great names: Euler, Lagrange, Plateau, Young, Laplace. They defined the problem. They gave first basic solutions. But then we have a Fields Medal, Douglas, who in 1933 gave existence proofs for given contours, and Radot, of course. Many others worked, but Courant spent a great deal of work on these, in particular inquiring about multiplicity of surfaces in a given contour and investigating this very problem here. Then, in more recent years, Almgren, Taylor, Bracken, and others, they gave fundamental contribution to static aspects, finding new solutions, embeddings in higher dimensions, periodic surfaces, and work is still going on. Not so many, but it's so fascinating that we were more than tempted to consider to do it, to do the same problem in the lab. Well, this we have to do it according to the Poisson-Laplace-Young equation that says that the pressure, the film surface, has to be related to the mean curvature of this surface, sigma 0 being the surface tension, and R1, R2 the principal radii of curvature of the surface. And before film, you are led to consider the jump on the two sides. The pressure is 0. The same pressure, of course, is air everywhere. And so this leads to the problem of a minimal surface, h equals 0. And so, you know, in Bicocca we don't have such a luxurious lab, but in the MTP in Cambridge they have. We talked to Ray Goldstein, who became immediately interested in that and actually did a lot of work on the problem I'm going to show you. So the problem is to realize the deformation that I told you, going from an unknotted wire to another unknotted wire made of a plane circle, and watching this soap film as going. And by watching in modern times, meaning buying probably 100,000 pounds of equipment, to have a camera, to have a very high-speed camera. So I'm now going to show you what is the result of our experiment, of Ray Goldstein experiment. Let me move to the movie. And here we go. So this is the starting point. And these are just the apparatus that keep the deformation under control of this wire. The wire is a very thin wire, and I show you now the movie. Here we go. Just pay attention to this. Let me stop for a moment. Well, this is just the hole, the throat that you see when you have the Möbius band deformation, so to speak. And then you will see this hole going to 0 as you are twisting and unfolding this wire. Pay attention to here. You see, this is beautiful. There is definitely something interesting in the fluid film. The soap film is still there and makes this twist that appears under our eyes. Let me show you another movie of this. This is just a zoom in, and let me start from here and pay attention to this region. This is the hole that is going to disappear as we untwist the wire. Here we go. And boom. And you see, it's very. Then we analyzed these images, and then we went to Bracke's surface evolver, and did some numerics on this. And here is a plot to show you just the comparative results using ruled surface analysis in Mathematica and the Bracke's surface evolver, because we know the border. And the border is given by the kinematic equations I showed you before. So we can follow this evolution rather well. And the minimal surface evolution at a certain point departs from the approximate evolution given by the ruled surface for a quite good piece of time, kinematic time here. The two curves are pretty close, but definitely there is then a change. And the twisted saddle, as it appears in the ruled surface analysis, is well capturing the local geometry that we see in the numerics. So, comforted by the realization in the lab and exploring and viewing many times these experiments, we were able to pay attention to local analysis on the ruled surface. And at a certain point, you can figure out that there is a point, more or less at 2/3 of your kinematical time, where inflexion-free stage is reached. C equals 0 again. And so again, we have near an inflection point a twisted geometry that appears. And if you pay attention to the 2D evolution of this ruled surface, here we are at the inflexional stage, you see that these represent a sort of 2D Rademaster type 1 move. Now, this hidden singularity is not playing a big role because, again, is the same singularity I showed you of the torsion, which is integrable, and so it gives you a continuous deformation of that. You can do some more analysis on the twisted fold, and we believe to have found for the first time a realization in fluid mechanics of a once called catastrophe, a twisted saddle catastrophe. And this is the algebraic expression for that. Now, you can conjecture a number of things, and for example, being 2/3 the point where there is this inflection, you may think that the process is leading you from a smaller area to a larger area before, and then there is a conversion of these two areas after that. Well, one interesting thing is that there is definitely a change in topology. The change of topology of the surface. So what about the close-up view of what's going on, of this emergence of this twist fold? Well, think of this red line as the line almost against the wire, made by the soap film just against the material wire. That is called the plateau border. So let's call the plateau border this red line, and consider the change of this plateau border before and after. If you pay attention to that, you'll see that in this case you have an approximately writhe 1 and twist 1, which gives a linking number 1. And after, you have a writhe that is approximately 0 with a twist that is approximately 0 and the linking, self-linking 0. A before and after. So this leads us to the fact that you definitely have a change in topology represented by the change in linking number, self-linking number of this virtual ribbon, the ribbon made by the central line, so to speak, the wire, and the other edge of the ribbon, the red line, being the plateau border. And this is the beautiful picture that shows you that the plateau border, the very green line here, goes up and flips over the other side. Now, quite interesting thing. I think the soap film twisted fold is something of an angelic character compared to the plasma loop destabilization that we discussed before, at least in terms of energy. So here, probably devil plays a more robust part because the dramatic change that is involved here is leading to a dramatic release of energy. So from angelic twist falls to devilish twist bursts, this is the end of my story for today. Thank you. Thank you for watching. I take questions, of course.
Any questions?
I've got a comment. That change in linking number of 2 is very interesting. I mean, that's what you see in DNA when you take duplex DNA and pass it through itself. You get a change in linking number of 2. So it's like taking this pair of curves, the plateau and the other one, and passing that pair through itself. That would give you the change in linking number of 2. So.
Well, thank you, DeWitt. I kind of knew this, but I never thought about it. And so I do thank you very much, because I like this analogy very much. And I'm now, first time, realizing what you're saying that is true for DNA as well. Interesting, indeed. Evidently, for this change, the surface, I mean the surface, in this case, the ribbon surface, so to speak, between these two curves, plays a very important role in allowing this recombination, isn't it?
It's not like a recombination. It's like when topoisomerase passes DNA through itself. And if it's duplex, then you get a change of 2 every time that strand passage happens. So It's like here you're passing like the entire ribbon through itself, in a sense. To pass from the linking number equal 2 situation to the linking number equals 0.
Okay, yes. Yes, definitely very interesting.
Can I ask something related as well? Do you have a change in the linking number in the case where you in the solar burst? Did you have a correspondence there, or not directly?
Well, no, definitely you have a change in linking number in general, because you have a change of topology, and if we talk for simplicity about Gauss linking number, then definitely you have a complete change of Gauss linking number. If you think of self-linking number for, say, one single flux tube that is reconnecting and exchanging parts of twist during reconnection, we know, this gives me the chance to say that we know his work with DeWitt Sumners and Christian Lang, that writhe remains conserved during reconnection of a single structure, assuming antiparallel reconnection. Well, in that case, I don't know of any work that precisely address these questions, although work on reconnection on flux tubes with internal structures, so to speak, has been carried out recently, and numerically, I mean, by numerical simulation. So it would be, for example, David Pontin is one that comes to my mind, but I don't know if there is any investigation of possible jump in self-linking number. But definitely linking number in general changes with a change of topology, sure, and that is has been measured, helicity changes, yes. The question in recent years has become to investigate in far more detail what happens. So if 10 years ago that was enough to say, change in linking number, nowadays people inquire about what happens to twist, writhe, etc. How energy goes in terms of twist, for example, would be interesting. Definitely. And it would be interesting for both fields of research. I mentioned astrophysical flows and for fusion. And for fusion is dramatically important because they want to have a process where you inject a lot of energy into the system up to a point that the system starts to be self-sustained. So in order to inject energy, you have to control the field. One way to do it is to control it through twist, because the poloidal contribution would control somehow field lines, but injecting poloidal fields and so twist makes it unstable for lots of reasons, and presumably also because of what I showed you. So that is also a very important practical problem to understand the role of twist and self-linking in relation to change of energy. Yeah.
Okay. Any other question?
Actually, Renzo, I have a question. This is Jean-Luc.
Oh, hi. Hi, Jean-Luc. Hi.
Hi. So you have a reconnection criterion, is what I understand. This criterion you give tells you whether something is going to reconnect or not. Is that in the plasma, in the solar flare case? You showed a picture and you have this, if I remember what, a twist criterion or something. Is that right?
You certainly do have a measure of a critical twist, which is called the kink instability, to say when something like this takes place, when a braided distribution of plasma loops get kink unstable. Not necessarily twisting up, sorry, but as in the picture, but certainly breaking up. It is curious to notice that so you have an exact analytical expression for this critical twist. And it is interesting to notice, we go back to Faraday, who pointed out the analogy between magnetic fields, so to speak, and elastic strings, reported by Maxwell, that also in elastic systems, you have what is called in engineering writhe instability. Once I talked about this to great people in elasticity, and I call it Zajac instability because that was the name in literature used, and many people objected and said, oh, surely Kelvin had to know this because of the deployment of the telegraphic cable. You know, you unroll the cable in the ocean and you don't want to get it twisted up in water. So he probably thought about that. Anyway, there is a history about that too. So when you compare the two critical numbers, you find that in the incompressible limit, this critical numbers are almost the same. So this is quite interesting. I think it's not very well known, but I found myself many years ago this. You can just one line of algebra. You can show that the kink instability is more or less in incompressible limit expressed in the same formula for elastic systems. Again, about the 2 full turns would give kink instability for a magnetic flux tube of dominant axial field.
The 2 full turns, that's
on this.
2 full turns would be linking number 2. I mean, so the linking number 2 comes in again here. So what's magic about the number 2 here? So.
Yes, good point.